Hello everyone, welcome back to day 3 of the Daily Study Group series. We are going through Etienne Bernard's Introduction to Machine Learning book. Today we are going to talk about regression. I hope so far the series has been helpful. Going through the first few chapters, we started out the basic overview of what machine learning can do and talked about some machine learning paradigms, especially supervised learning, unsupervised learning, and then there was also reinforcement learning. We started with supervised learning because that's the most common form of machine learning you will encounter. Yesterday we covered classification, where you can use a machine learning model to assign labels to a sample based on some training data that you've already seen. So a lot of places, including our own image identify function, where you have to look at some data and come up with a label, like, is this an image of a dog or a cat? Is this an image of, something that's maybe a medical image that requires further input from a doctor, or can be ignored as like no issues there, whether it is your email inbox where you're trying to see if this email if your email system is trying to flag something as spam or not. You're trying to answer a question of the type, is this A or B, and that is classification. Provide a class. Beyond classification, there is another supervised machine learning approach, which is regression. That's the focus here. The question is slightly modified here. You're still trying to predict something, but instead of a class label, which is like a categorical attribute or a nominal attribute, usually represented by a string, instead of that, we are trying to predict a numeric value, price of a home, age of a person, weight of an animal, runs scored by a player. So the answer has to be a number. You cannot do regression for categorical variables or nominal variables. Now, can you switch from one to the other? Can you reframe a classification problem as regression? Maybe you can. Can you reframe a regression problem as classification? You can, if you choose to give up the granularity at which you want the numbers. So maybe if you can discretize the numbers and not have a continuous range of values, and you're happy to put things, samples, into bins, into groups, and then you assign labels to those groups, you will be able to reframe a regression problem as classification. All right, so let's jump in. Hopefully we can go a little bit more through the code, but as always, we are happy to take questions. So if you've already been able to read the chapter and you have questions, we'd love to hear from you. And I'd love to hear whether or not you've been able to read this chapter. I see a question from Matthew about questions being asked and answered. Yes, in the Q&A pane. So sometimes we will answer the question and publish it, so then everybody can see it. In fact, maybe today, Luke, we can try to publish more of the questions. And if we do not publish, the answer goes directly back to the person who asked the question. So if you are asking a question and we answer it, you will see it, but maybe the others won't be able to see the answer unless we publish it and we decide intentionally to share it with everyone. Okay, so we have few more people who have read the chapter. That's fantastic. So in these first few minutes, I'll be happy to take any questions you might have about the stuff you read in the chapter. And if it turns out that I'm already planning to focus on that particular bit, I will hold off on answering your question. Or if it's something very specific that I am not quite covering today, I'll try to get to it right now as I try to answer the question. So the published answers should appear to the right of the browser window. As questions are asked and Luke answers them, or I tried. Sometimes if I answer them live, then we will not type in an answer. But if Luke is answering a question and he's typing in and providing an answer, it should appear to the right of your webinar browser window. Okay, while you're reviewing some of the content that you read in this chapter on regression, let's ask a quick question about classification. So here, appearing on your screen, I have a couple of options, a couple of problems that you might want to solve using machine learning, specifically the supervised machine learning task of classification. So which of the following problems do you think you can solve using classification? And I believe you can select more than one options. So when I am trying to decide whether or not I want to use classification, I always try to see if I can rephrase my problem as a question, is this A or B? Can I come up, can I pose the problem as a question of categorizing my samples as belonging to class A or class B? Or class A, B, C, D, E, F. Really, I can have as many classes as I would like. Okay, I'll go ahead and share the responses I've received so far. So let's pick each problem um, at a time. Labeling images of tissue samples as malignant or benign. Right? You have image of a tissue, microscopic image of a tissue sample, and the algorithm has to label them as malignant or benign. Easy question, right? A or B, malignant or benign, class A, class B. Definitely something we can do with classification. Predicting the Lexile score of a book. So Lexile score is this score, I believe you provide. It's anywhere between 5 and I want to say 900. I might be wrong, but basically it's a numeric score you assign to the level of the text, that how advanced it is, at which grade level a kid might be reading that book. It's a numeric score, and it can be anything between 5 and 900. So being a numeric value, this is a good candidate for regression. You really have you cannot quite unless you have like one class for each of the values from 5 to 900. This cannot be a classification problem. So this is a regression problem. So this is not classification. Third option, predicting the correct grade level 1 through 8 for elementary and middle school students based on different measures of academic performance. Now, although it's a grade 1 to 8, they are actually just classes, right? Class A, B, C, D, E, F, G. So then this is assigning that particular class to the student based on what sort of math they're doing, how they're doing in science, what are the topics they're covering. So this is again a classification problem because you're assigning that class or category to that student. Visualizing samples with 10 features or attributes in a two-dimensional plot. And the keyword here is dimensional, right? It should have triggered your memory for dimensionality reduction, which is an unsupervised learning problem. Basically, we're not dealing with any sort of labels here. So there is no question of is this A or B to be answered here. You have some sample, it has 10 different features, height, width, color, maybe I don't know what it is made up of, things like that. Now, based on these 10 features, you will be making decisions, but sometimes during things like exploratory data analysis, you want to get a feel for the data. You want to see there's some sort of organization in the data. Some of the samples belong to a certain group or the other. And for a quick visualization, what you can do is reduce those 10 features to a pair of features, which can then stand in for XY coordinate values, and you can use those numbers to visualize the feature or to visualize the sample in a two-dimensional feature space. So this is unsupervised machine learning. There's no way you can use classification here. And finally, autocompletion of email text. Although it seems like you're generating text, you're not quite generating labels, but you can think of as what is the best completion. Each word that can be used to complete a line of text can be thought of as a label. And so the automatic completion of text is a supervised classification problem. Let's do a quick review of the chapter through questions, right? So I'm hoping you had a chance to read through it, or at least if we've been talking about regression. So let's start off with some simple questions like, what sort of question can regression help answer? obviously not one of the options because we just talked about it for classification. And the answer is right here in this very first paragraph of the chapter. Okay, that was quick and easy. How much or how many? Because you're trying to predict a numeric value. That would be the answer to the question, a number, how much or how many. Cannot be is this A or B because that's classification. How's the data organized? That would be clustering. And is there something weird or out of ordinary? That would be anomaly detection. So here in regression, the goal is to predict a numeric value. If you've been looking at some of the examples here in the regression chapter, whether it's cars stopping distances or the Boston Holmes dataset, you have a feel for the kind of data set that lends itself well for the task of regression. So which of the following do you think has to be true so that you can actually use regression? Do the data samples have only numeric features? Do the data samples have both numeric and nominal or categorical features? Do the data samples have categorical class labels? Or do the data samples, I'm so sorry for the typo there, misspelled samples, do they have to have numeric values that need to be predicted? And again, I think you can select more than one option, which is a hint that indeed there are multiple choices here that must be true to use regression. That was wonderful. So 44% pick data samples with my typo in there must have numeric values to be predicted. Easy. That's what we've been talking about. Now from the rest, data samples must have only numeric features? Not really. Right? You have to have a numeric feature or numeric value that you want to predict, but the rest of the features, do they have to be numeric? No. They can be either categorical, nominal, or they can be numerics. You can have a mix of both. You can have only categorical attributes and still predict a numeric value, like predicting the lexile score of text, right? You have only text, and you can derive numeric features from the text. That's what you might do with feature extraction, data pre-processing. But you can have any sort of features, any type of data, and still predict a numeric value. So the right options to pick would have been 2 and 4. So data samples can have both numeric and nominal features, and they must have numeric values to be predicted. And a last question for this section. Not really. I think I've covered all. All right, so let's then jump into the code. Again, you can download the notebooks. I hope you have, because it's just so much more fun to be actually able to work with the code as you're reading through the chapter. So we'll start out, let me consult my notes quickly here. We will start out with the car stopping distances dataset. Again, note that we can get it out of the data repository, the Wolfram data repository. So if you just copy that and run it, you will get that data here, and you can see it's a pretty simple data set. You can see it has 50 rows, 50 samples, and has two features, speed and distance. And we can frame this problem as in two different ways. We can use speed as an attribute or a feature and try to predict the distance, the stopping distance needed. Or if we wanted, we could use distance, the stopping distance, as a feature and attribute and try to predict at what speed this vehicle was traveling. Let's pull out the code and see what's going on here. Again, we have some iconized code. If you remember, this is only to not distract you, because this is the important part of the code where you're getting the data set. I think here the iconization is only for this attribute of the data set, saying that max items is just 8. So you don't have, an overly long representation or visualization of the data here. You just have 8 rows at a time, and then you can page through it. We're doing some very basic exploratory data analysis here. We are putting it into list plot, which is your Wolfram language function to quickly create a scatter plot, two-dimensional scatter plot. So if you have two values, two features, you can quickly create the scatter plot, and you should be able to visualize if there is any relationship between the variables. And we clearly see the relationship here, that if the speed is increasing, if the vehicle was traveling at a much higher speed, we see that the stopping distance has increases as well, and we see the trend here. What's going on here? Could we have just used list plot data set? Yes, we could. It will give you a very apparently it's not happy. Why isn't it happy? Let's try and type it out. I just said yes you can, and then it refused to cooperate with me, and these things will happen. Okay, let's run that one more time. Oops, didn't mean to do that. Okay, I'm going to leave this out for now, and I'm going to have my data set, and then there you go. Some weird issue happening there. Just sometimes playing around with the code, maybe reformatting it. If you're facing the same problem, you can take off that the extra bells and whistles that are intended to make this look pretty for the book. You can take that out, and you can see that now it's really a matter of just feeding in the data set into list plot, and you immediately get the a nice visualization. What I always hate about visualizations like this is no access labels. That always makes it so hard to figure out what is going on in here. So there, the frame label was an important thing to put in there. We put in for the x-axis speed and for the y-axis distance. And then we also put in some we customized. We were not happy with the little dots, so we went for the unfilled markers here. We set an image size, and so on. But all of that is really not important, and that is really kind of the reason why this was iconized, to hide it all from you. That's not really important for machine learning, for regression right now. But I did want to point out to you that when you do that customization for visualization, you might sometimes lose out on some default features we've built into visualizations in recent versions. So for one, I really like this interactivity in the plot right now, where you can hover over each data point and it will show you the values. So I can easily see here that this had an x value of 18 and a y value of 84. All right. So here we have a nicely formatted representation of that same data set. I could have worked with data set, but just like classify, you can go over to the documentation for predict. Predict is the main Wolfram language function that you use for regression. And it's the workhorse for regression, has an insane amount of options available, some built-in predictor models. The documentation is really rich. I think you can just do a course on regression just with the material in the documentation and the examples in there. So I hope you're able to go through those. And you can see you can have the training data in structure similar to classify, where you can have in-out pairs all listed together, or you can have all the inputs, all the features of the samples in one list and the output values in another list. Or you can have the setup like this, where you have the data set and you just mention which column has the value that you're trying to predict. So here we have that the first option, the first way to structure your input data. So we have the speed, and then we have the stopping distance. If you're wondering about the slightly different formatting that you're seeing in your notebook, this doesn't look like just the number 4, right? This looks something different. It's because it is formatted as a quantity object in Wolfram language. And if I copy it out here and I show you the full form of the expression, you will see this is how it is represented. It's the quantity 4, and then it has miles per hour. Okay. Turns out that all our major functions can transparently work with these special objects, quantities, dates, and so on. So you do not have to really worry about, they are just much more interpretable as you look at them. This makes more sense, 4 miles per hour. You look at it, that's speed. If I had only put in the number 4, you might be left wondering, is this 4 meters per second? Is this 4 kilometers per second? Is this 4 miles per hour? So it's sometimes really useful to have quantities instead of just numbers. So I can have all my input training data set up, and then I run predict, and the progress indicator popped up for just a little bit. As with classify, I get the predictor function, and I can open it up and I can see some details. I can see that it deduced that all the inputs were numerical, and it's decided to use linear regression, very well established method, and it used just 50 training samples. So now that I have this predictive model, I can give it some new values, say for example 23 miles per hour, and I can have it predict predict the stopping distance. And you might have noticed that the output changed slightly from what I had when the pre-evaluated version of the notebook, and that is quite possible because there's some randomness involved in the process where the predict function is trying to go through different methods and trying to pick which method works best. So you might not get exactly 72.3482. You might get a number from a distribution of values, and you can actually see that. We'll do that in just a little bit. Here you see that predict not only returns the predicted value, but you can also get things like distribution, just like in classification, where you not only you were able to get the predicted class label, but you could get the probabilities for those class labels. So in this case, you can get the predicted output value, but you can also get a distribution, and we'll look at that in just a little bit. But let's first plot it. So here you see with the little markers, we have our initial scatter plot, and we have superimposed on that the plot of the function, the predictor function that we have here in the form of distance. You can take apart this piece of code. So show here is Wolfram Language visualization option to show graphics with specified options added in. Like you can include two different graphics. You can include a plot and a list plot. That's exactly what we are doing here. This is our first plot, and this is our second plot. So you can just pull out this plot by itself and see what it looks like. We didn't even get a plot here. What's going on? There's some issue with the formatting in this notebook for some reason. I might have to work on that a little bit, but let's see. So let's try and do this, right? We've seen that distance is able to work fine here. So if I put in just a number, distance is able to handle it and give me the output. So 10, if I had 10 miles per hour as speed, my stopping distance would have been 22. So now what I'm trying to do in plot here is vary the value of speed from 0 to 30, and then I want to come up with the stopping distance for it. So I can pull this out, and I can try to see if this is going to work for a number of different values. So I can say speed from maybe 1 to 10, and it'll take the discrete values 1 through 10, put it in here, and give me the stopping distance for each of those values. This is a little crazy. So, for 1, 2, 3, 4, 5, you're getting negative stopping distance. So this should work. What I want to do instead of table, I want to use plot, and I want this to go from, let's say I'm going to take this from 10 to 30. Not quite getting it. I might be having trouble with quantity here, so I'm just going to go with speed. It's not working either.
Hey, Abrita, I was having trouble with that too. Use the quantity magnitude around the distance, I believe.
Quantity magnitude of
Yeah.
Oh, I see, because distance is trying to come back with a quantity as well. Okay.
Yeah.
And plot is not handling quantity. I see. Thank you so much, Luke. There you go. All right. So if you have, I did claim that most of our functions work very nicely with quantity. Sometimes there are issues. So if you want to just stay with numbers and not go into quantities, that's great. If you have trouble working with quantities, as the name suggests, quantity magnitude will pull out just the magnitude of the quantity, just the number of the quantity, and this should work. So as Luke suggests, we can just try to get quantity magnitude out of the distance here. And that should give me my nice function here. And again, with the new interactivity, you can actually hover over the line and see the values. And, again, we can fix this as well, because if I run it right now, it won't give me the visualization that I'm trying to get. Oh, okay. Let's pull that out. Let's make sure that's working. And did I change data plot? Okay. There you go. Okay, so we are able to see that the model it came up with, linear regression, is really a good fit for the data. This brings me to a question I think I encountered both in chat and I think also on the community post is what is kind of commenting on the difference between statistics and machine learning. In the context of regression especially, when you show this to statisticians, they often are like, well, we've been doing regression for ages, and then what is this newfangled machine learning that seems to come up and suggest, oh, we use regression? I think the difference lies in the goal of each approach. With statistics, you're using the regression model to kind of find something that best fits the data, that best explains what is happening in the data. With machine learning, you're using the same algorithm. You're still trying to find a regression model, but the goal is to come up with a more generalized model that makes better predictions. So if you have this function here, that is a regression model, now if I give it an x value, I can come up with a y value. And the more generalized my model, I can come up with a better y value that is in keeping with the data set that I've observed. So I mentioned that you can not only just get the number, the predicted number, but you can get a distribution for the number, and you can see it comes up with a normal distribution with a mean of 72.34 and a standard deviation of 15.36 feet. And I won't go into the details of the plot here. I can see that we are having some issues with quantity and quantity magnitude, but you can see it's just a visualization of this distribution. If you are running into issues, you can just definitely copy the code that you've been trying out. You saw some ways we tried to debug the issues we had. Luke suggested using quantity magnitude. You saw me pull out some parts of the code and leave out some of the extra options and try to run it. So try all of those things. If you are still facing issues with the code, definitely post on community and we'll take a look and try to debug it along with you. So one thing Etienne mentions is that it's very common for most regression models. They try to come up with a pretty simple model. And so you'll usually get a unimodal distribution. And more often than not, you'll get a normal distribution. But it might be possible to tweak the model a little bit to get a multimodal distribution. And here also, Etienne talks about, if we can go back to the chapter, as here towards the end, especially with that facial age. This example here is where we actually have this facial age classifier. It's a built-in classifier. So if I just take it out here. So if you give it the image of a person, this is a built-in classifier that has been trained on lots and lots of images of people's faces. It will try to give you the age of the person. So it thinks, this classifier model thinks he's 14 years old, and if I ask for probabilities, I can see that, I have discrete values of ages. I don't have like 1.5 years old, or 14-year 6 months, 14-year 9 months. I don't have that. I have just discrete ages. And so this lends itself to a classification problem. So either tell me age 1, 2, 3, and so on, all the way up to, let's see, 101. So it is trying to predict one of the 101 classes. Although age is a numeric feature, it's being treated as discretized into specific values, and that is being used for classification. So this is one way where you can, move from regression to classification. You can, in our car stopping distance example, you could go from, you could discretize the stopping distances into something like low, medium, high, where 2 to 10 feet might be low, 10 to 20 feet might be medium, 20 feet and more could be high. And then you could reframe this as a classification problem. I hope that makes sense. Okay. As usual, no unanswered question. Thank you so much, Luke. You do a fantastic job of keeping up with those questions. All right. So now let's move on to, again, another hello world sort of problem in machine learning. If you're starting out with regression, I'm going to skip brain weights. If you have any questions specific to this problem, feel free to get back to us on the survey or on the community thread. So we are going to look at the Boston Holmes dataset, which is again, very popular as you start out working with machine learning. It's easy to figure out. There are some criteria for these homes in Boston, and you're trying to predict the numeric variable as a median home price. In fact, if you want to learn more about it, you can go over to the Wolfram data repository, and it's right there. Of course, it's not there when I want it. It is a regression problem, but I can search for it. Here's the sample data, Boston Homes. There's some details here. You can read more about it. So home values for 506 Boston suburbs, the median home value with potential influential factors such as crime rate, number of rooms in the homes, distance to employment, and so on. And so here, if you go in, you can see code examples that show you how you can download the data, and then some examples of how you can, do some analysis. In fact, here's exactly a prediction example. And then there is also some source metadata that tells you, it's a pretty old data set, the original source of this data. Anyway, this is what the data set looks like. So let me go ahead and run it one more time. And then we can do exploratory data analysis. So let's pull this out and see. This is the, if I move through it, I can see this is the last column here. This is the median value of the home. And I can already, when I import the data in a data set, again, we are lucky here. We don't have to do anything like data cleaning, because being a data set from the repository, someone has taken the trouble of cleaning up the data set, putting it into a nice computable structured format, and I can just pull it in and work with it. I can already see that there are 506 samples here, rows 1 through 506 here, and I can see it has 14 columns. And if I just browse the data, I can see mostly there are numeric columns, and there is this just one column that says CHAS. I mean, it's just a name for the column. I don't know if it makes sense, but we can see it has something to do whether the tract is bound by Charles River or not, right? Other than this column, everything else is numeric, and we can take a look at the values here. And we can actually do something nice if you have things in a data set. When you get all the rows, you can also do some aggregatory operation on the values in that column. So I can directly get the mean of the value here. For other things, maybe like see, what else do we have? I thought we had a room, something that RM. So probably um, let's go with ZN. Probably that's like zone or something. So I'm going to change the column name to ZN from here. And instead of mean, I can use something like counts. And I can even sort it. So I can see, oh, it's not, oh, what I want to do is key sorted. Okay. So I can see that, for feature value for ZN as 0, I have 372 samples that have the value 0, and then all the way up to, let's see, for feature value 100, I have only one sample. Okay, and so I can also do something like, so let's see here, I would have gotten all the values for the median home value for this column. Instead of all, I can actually put in histogram, and it will come up with a histogram of the values from that column. So this is one way of doing things. The other way is where you just bring in the data and then feed it into histogram as you would do for a list of values or things like that. So here we can just get all the values for that column mid V and put it into histogram. And if you're wondering what is this 50, you can click here and see that it's the specification for the bin. Specifically, you can put the bin width. So I want a bin width of only 50, and you can see the difference here. Right? If I didn't specify the bin width, the system came back with whatever it thought was the best bin width. I think I have 10 here. So, 10, 20, and so on. But here I would like a bin width of 50. And here is a histogram of all the median values. So I can look at it. And then I believe Etienne comments in the book about what you could infer. Seems like all the prices are positive in a similar range, so we don't really need to do too much of pre-processing. Then we also look into this CHAS feature, which is not numeric, right? And so, oh, he's doing exactly what we did before. He's doing it in this way. There's another way of doing it. So just like all other programming languages, there's more than one way to do something. And I can see that has only two different values, whether it bounds Charles River or not bounds Charles River. And we have fewer of one type and more of the other type. Okay, so some basic exploratory analysis, not too much, nothing very fancy here. So it gives us an idea. And now we can get into actually using predict here. So first we are going to break up the data set of the 506 or so samples into training and a test set. So we are going to take 400 of those into the training set, and we are going to drop the rest into a test set. Again, we have seed random here just to make sure that when we random sample, you and I both, we get the similar kinds, the same data sets for test and training. So let's go ahead and run that. And we can look at our training set. That's what we have. And let's look at our test set. There you go. 106. Okay. And now I could have just done something like this. Okay, and let the system decide what what it thinks is best for my data set. So when I don't specify anything, because I have no idea what would be the right method to use, or any other customization that I would want for my model, I just have this training data and I just want to use predict, I can do that. And it deduces automatically that it has mixed features. That is, and if you hover over it, it says, okay, I saw all these features when numerical, and then here was a text feature, and that was the CHAS feature, the CHAS column, and it automatically deduced it by itself. And it thought, the system thought that the nearest neighbors method was a good way to go. And so it went with that. And I can now try this on, let's see, did we have a test sample we could try it on? Here. So let's copy it over to my model right now, which is like plain vanilla model, and gives me a value of 39.25 as the median home value. Now let's tweak it, because Etienne says here that he wants to make sure that the training should take about 10 seconds. That gives it a little more time. It's saying that, you have time, take your time and explore more models. There's no rush. You don't have to give me an answer right away. Take your time, explore more models, and pick the one that is the best. And then also to be super careful that this variable is indeed interpreted as a nominal attribute, and it doesn't make a mistake of interpreting it as a numeric variable, because we can have such things, right? Like grade. It's 1, 2, 3, 4, 5, but it stands for a class. It's actually a nominal attribute. So we could do all those customizations, and we can run that very customized classifier. Let me name it PC, and let's see if I have any difference. Right off the bat, I can see that it's taking a longer time to train, which is perfectly okay. And it decided on a different method. It decided that gradient boosted trees, in fact, was the best way to go. And we can go ahead and see whether PC is actually performing in any way better. Very close. So my default classifier is predicting 39.25 value and 38.4681. I don't think I have this as part of the test set, so I don't really know what was the original median home value for this particular sample. But let me go ahead and show you what you can gain from the model, what all the information that you can extract. So you can run an information. Let's do this side by side. And compare the two models. Oh, they went there. See if I can. Nope. No, you won't show me next to each other. Okay. Well, I won't waste your time here. I was trying to see it next to each other. That would be possible. Okay, so let's just see here. My original model, we saw it use nearest neighbors. It had a standard deviation, which is kind of a representation of the error of 3.53 at a 95% confidence interval. It showed you batch evaluation speed, that when the classifier was being built, it was trying out different methods on different batches. It was going at this speed, and it takes about 5.1 milliseconds to give you a prediction when you give it an example. The model does not take up too much memory, but well, nearest neighbors would take up a lot more space than others, because for nearest neighbors, really you store the entire training data as part of the model. So it does take up some space, and You can see the standard deviation, how it changes, how the learning curve changes, and so on. But from a more customized model, turns out using gradient boosted trees, the standard deviation is comparable. It is using a single evaluation time was slightly longer. The batch evaluation speed was also slightly longer. The model actually takes up more space. So if that is a concern, you want to pick one method over another, and took a total training time of 14 seconds, whereas this one took a training time of 2.49 seconds. So a nice example of what you can do, try out different methods, try out different parameters or different options. One piece of information you can get from information is that is not immediately shown here, but you can always go into the documentation for information and see what sort of information you can get from a model. One is feature type, and we can see how it interpreted the features, is interpreted everything as numeric except for this attribute was interpreted as text. All right, so just like the previous model, you can also get the distribution, but one more interesting thing, and we've seen this for classification as well, is the SHAP value, which kind of gives you an idea about the importance of the feature. So I can look at features like crime, which is probably the crime rate, and the zone, and I can ask for the SHAP values, and I can see how important that feature is in this prediction. So here is a plot of the average number of room, how the value of the home changes based on the average number of rooms. And one thing Etienne points out here, that it's not causal. By no means is just like adding the number of rooms is changing the value of the home. This is more as correlational, and this is just something you're observing in the model. Moving on quickly to some other things you can get, like some other information you can get from the classifier or the predictor model. So information gives you just the basic information from the model, but you want to see how it performs on other test data. So in that case, you will need predictor measurements. So let's go ahead and try to measure the performance of our default classifier, which was using neural networks. So I'm going to go ahead, which was using nearest neighbors. I'm going to go ahead and run predictor measurements. To run predictor measurements, of course, you need a test set because you want to compare the predicted values against the original values. And we can see here we used 106 samples for testing, and this was the standard deviation or the root mean square error. And then this is another interesting visualization. Is kind of comparable with the confusion plot matrix that you saw, or the confusion matrix plot, sorry, for classification, where you saw what was the original label and what was the predicted label. And so here you can see this was the actual value, and this is the predicted value. So you can see whether your predictor is overshooting or undershooting, and how well it aligns with the original value of all the test samples. Some useful things about this sort of a scatter plot, and in fact the right name for this is comparison plot. So you can I think go ahead and say that you want the comparison plot. Oh wait, there you go. And it will give you just this visualization instead of that all the details involved in the report. So you can just take a look at it. Okay, you can also get to the worst predicted examples here. I'm looking at the 2 worst predicted examples that it did really bad on this, and then you can zero in on that and really analyze those particular samples and see what happened there. So yeah, that was kind of like a basic overview of how you can use predict with data. I'm sure there'll be lots of questions, so I would really encourage you to, for regression or even for classification, both chapters, open up this code notebook and then try to run all the examples, make changes. And if you have any questions, bring them to us on Friday, post them on community. We'd be happy to walk you through the code, especially for our beginners. Just like classification, Again, to improve the ability of your regression model, you can use sort of similar strategies. And I think that's what Etienne talks about here. Strategies like you can definitely use more data. You can try to get more diverse data to have your model be a better representation of the real world. And it is worth trying all these different methods that you can see in the documentation for predict. So let's go back to predict. You can see all these methods are already available. You can have decision tree, gradient boosted trees, of course, linear regression, nearest neighbors, neural networks. So this is slightly different from a neural net framework that you might have seen where you use net model to download a model or create a model. This is a pre-built sort of architecture that you will use for this particular prediction problem. It's a numeric prediction problem, so there is a model that was created. It will just use this data, be trained on that data, and give you some results. Very little customizability available here. To work with a full-fledged neural network, you need to use our neural net framework. It's worth going through these options here and trying different values of these options to see whether you can tweak the model. Absolutely okay to go with the default model that the system comes up with. For this example, you saw that it performed as well as the other customized model, so that should be absolutely fine. All right, so I see lots of questions came in, and Luke has been keeping up with those questions. Okay, I do have a few review questions for this part of the study group. So let's start with this question. Is it possible to convert a regression problem into a classification problem? Glad to see 77% of you agree that this can be done by discretizing numeric values and assigning a label for each group of discretized values. I mean, you could treat each numeric value as a categorical label, but as we saw for that age classifier, for that image age classification problem, let's see if I can pull that up here. Right here, right? So we went with one class label for each of the 101 age values we have here. It can be a little cumbersome. So the right approach would be to discretize the numeric values. You don't have to worry. I mean, um, about this first option here. Yes, of course, numeric output cannot be converted to categorical labels, but you can rephrase the problem as something like this and then work with that. Okay. Let's see. Question about performance measure, because it's always important to evaluate the performance of your model. Creating a model is always so much fun, but then to convince others that your model is really good, or before you release it into the wild, you want to assure yourself your model is doing things the way you expect it to do. So evaluation is very important. Predictor measurements is the function you want to use. Which performance measure do you think will allow you to quickly visualize the predicted values against the true value? And so really easy way to visually see quickly whether your model is providing useful values. So, I mean, all are valid, almost all are valid performance measures. Scatterplot is made up. Scatterplot is, what we call a scatter plot can be created in Wolfram language with functions like listplot, but for predictor measurements, the specific term you have to use is comparison plot. I think we did that. Sorry for all that scrolling. There's a lot going on here. Here. For predictor measurements, the option is comparison plot. I was going for a visual performance measure, and that would be comparison plot. RMSE and residuals are also useful. In fact, I think we have here a histogram of the residuals, or just a plot of a histogram of the residuals you can see here. But I was going for what you can quickly get from the predictor measurements objects, and that would be comparison plot. All right, and I have one last question for you. Which of the following would provide a quantitative measure of the deviation of the regression model from the truth? So another performance measure. And this time I'm not really asking for the exact option name. So even if you are calculating this on your own, writing your own code, writing your own function to calculate this, I'm just asking for what do you think would give you a quantitative measure of the deviation? So root mean squared error, sure. And I would pick also mean squared error, right? Root mean squared only makes it, in the magnitude of the residuals. So mean squared error kind of amplifies it a little bit. So, but it still is a quantitative measure of the deviation, right? And the residual itself definitely is also letting us know how far it is deviating. Mean of the residuals, not so much. And in fact, we have Etienne also talking about it because, the positive and the negative residuals will cancel each other, so you won't get that information. And then comparison plot is great for a visual interpretation, but not as useful as a quantitative measure. So I would pick residuals, mean squared error, and root mean squared error. All right. So that's it for today. For once, I think managed to finish on time, just 4 minutes. I mean, not really on time, 4 minutes overboard. But I hope that was useful. We definitely were not able to get into all the details discussed in the book, but one of the reasons I really like this book is written along the lines of elementary introduction to Wolfram language. Definitely a lot of guidance from Stephen Wolfram as Etienne wrote this book. It's very practical. A lot of machine learning theory books will not walk you through the practicalities of using the model, and given the fact you can combine the code right away, it's written in a style of a computational essay, you can just edit the code, rerun it to test your understanding. Really makes it easy to get into machine learning, to kind of test things around very quickly. And so I hope you have a similar experience as you're reading this book. If you have further questions about the code, again, please don't hesitate to bring it to us. As I close out the session, you'll be directed to the survey. So if there is a specific topic you want to review on Friday, we'll be happy to do that. Type it in to the survey report, to the survey form, and it will let us know what questions, what topics we should focus on. And if you have anything for that matter that you would like to let us know about, what you like in the study group, what is not working for you, we would be happy to receive that feedback and take it into account for our future sessions. So hope you have a fantastic rest of the day. Thank you so much, Luke. Cassidy had to leave a little early, but we'll close the session without her. She'll be back again helping out tomorrow. She'll be back with the quiz link, any other resource links that she might have for you. Definitely go check out the community thread. I know there are 4 posts there, but I'm hoping to see more posts as you read through the chapters, as you try different codes. And don't hesitate to post on community. Everybody is a learner here, and it's a very, very friendly community. We have moderators who do a fantastic job. I've never once seen anything negative, anything hurtful on community. So lots of experienced users there who would be able to help out. So if you have any questions, don't hesitate to post it there. And you can also go and check out all our other groups we have on community. So if you're interested in things beyond machine learning, you can go to the groups tab and see what else is there, and you can look into it. So someone posting about some computational humanities data, you might be interested in this group. So all right, hopefully you have a wonderful time for the rest of the day, and come back and see us tomorrow for chapter 5 on clustering. So we'll start unsupervised machine learning, and it's really one of my favorite topics. So hopefully we have a fun time discussing it. Thank you so much. Thanks, Luke. See you tomorrow.